Yeah, so it's chapter 10, electrical circuits, and these are the practice questions. And what I'll do is go through them and just show you the question and then the answer that I've done, and any valuable, amazing insights that I have into these things. So, question one. 3 resistors, 10 ohm, 20 and 40 ohm. What's the minimum possible resistance? Minimum is going to be in parallel. So we go this. 1 over the total resistance is 1 over 10 plus 1 over 20 plus 1 over 40. I just type that in as I go. Can you see this? You can't, can you, on the video? But if you just type it in, 1 divided by 10 plus 1 divided by 20 plus 1 divided by 40 equals, you get this decimal if the mode on your calculator is the right one for the job, and it's 0.175. Take the reciprocal of that, and that gives you 5.7 ohms to 2 sig figs, which is what these numbers are here. It says, what's the maximum possible resistance? Well, you put them in series, don't you? Add them up. B, the filament lamp is connected to a power supply and it glows at its maximum brightness. The output voltage from the power supply is halved. Why doesn't the current halve? The reason is that the maximum brightness, the filament is very hot, so it'll have a much higher resistance than it does cold. When the PD is halved, the temperature of the filament drops, so its resistance drops. So the current doesn't reduce by half; it reduces by less than half. That's not. So it's really important that we write here it reduces by less than half. In other words, it might drop down by a third. Let's say. You see, because the current, more current will flow per unit volt because resistance is less because it's less hot. Question 2. What do we got? Calculate the total resistance. Easy peasy. Add those together. 360. Do the in fact, this is the same, the values are the same as in question 1, so you do the same thing. Look, here I've done here. You can stop this video anytime, don't forget, and just think about it, catch up, nod off for a bit, then come back. Question 2, I tell us state one electrical quantity which is the same for both resistors. For here, it's the, what is it? Yes, it's the current, everyone, because it's a series circuit. For here, it's the PD or the EMF, the PD you should say, because they're in parallel. So the PD across these 3 resistors is exactly the same. I'm doing this pretty fast if I can here. Let's just see. Calculate the total resistance for B. Oh, we did that. Oh, did it. Done. All done. Next, question 3. The supply has 8.2 volts. Calculate the total resistance of the resistors. What does it show? We've got a diode and then 2 parallel resistors and then an ammeter, 8.2 volts. Calculate the total resistance. It's the parallel combination, isn't it? 1 over 100 plus 1 over 180 gives us 0.015 recurring, and then taking the reciprocal of that gives you 64.3 ohms to 3 sig figs, because that's what we've got, these resistors. The current measured by the ammeter is 100 milliamps here. Calculate the potential difference across the LED. 3 marks. 3b. First of all, we want to say we can calculate V equals IR, 100 milliamps times 64.3. That's the parallel combination of these 2 resistors. And that gives us the PD across the resistors, 6.4 volts. If that's the PD across the resistors, right, because they act as one resistor, so we can do that. The resistor, the equivalent resistor is 64.3 ohms, and the current through that equivalent resistor is 100 milliamps. So that gives us that. The remaining of PD of the 8.2 volts will be across the diode. So you take away 6.4 from 8.2 and you get 1.8 volts. See it across the LED there? Calculate the total power dissipated by the resistors. P equals I squared R is the easiest way to do it. Our I is 100 milliamps. I'm writing 100 times 10 to the minus 3 squared. It's milli is times 10 to the minus 3 times our 64.3 ohms. Gives us 0.643 watts, 3 sig figs. If you wanted to do it the harder way, or the a different way, there's an alternative. You could go V squared upon R for power, and then go. You got your 6.4, the V across the 100 ohm resistor, and the V across the V squared across the 180 ohm resistor gives us those two numbers, which adds up to the same answer as that, to 2 sig figs this time, because my voltage is to 2 sig figs. Let's remember our sig figs, everyone. Question 4, the two rules. First law is the sum of the currents into a junction is equal to sum of the currents out. Second law, sum of the EMFs around a closed loop is equal to the sum of the PDs around the closed loop. B, this is what we've got. It says calculate the current in the 750 ohm resistor. It is going to be the current in the 750 ohm resistor is just that's Kirchhoff's law. You're just doing isn't it? The current in the 750 ohms will be the 0.030 amps flowing through R1. Out of R1, 0.010 amps flows through R2. Therefore, 0.020 amps has to flow through the 750 ohm resistor. They join up here and go around there. Next, the PD across the 750 ohm resistor. Once you know the current, you can do the PD. It is going to be current PD, V equals IR. That is 0.020 amps times 750 ohms, just 15 volts. The resistances R1 and R2. I've called it 4C, but it's III. V equals V. So R1 is V over I. That's 45 minus 15, because we've got our, why am I doing that? Let's have a look. 45 volts there, minus 15 volts. 15 volts is across 750 ohm resistor. So R1 is going to be, R is V over I, is the V across R1, which is 45 minus the 15 across this resistor, gives us 30 divided by the current 0.030 amps, which gives us 1000 ohms. And R2, this one, is going to be, we want our 15 volts because that's in parallel with the 750 ohm resistor, so it'll have 15 volts across it as well, divided by this current, 0.01 at 0 amps, gives us 1500 ohms. Get it? Question 5. Question 5 is how the resistance of a thermistor varies with temperature. There's the resistance temperature. As the temperature goes up, the resistance decreases. It's inversely proportional. Thermistor is used in the potential divider in circuit figure 5 here, to monitor the temperature of an oven. 6 volt DC supply, 0 internal resistance. So in other words, what the question's telling us there is internal resistance isn't part of the question, and the voltmeter has an infinite resistance, which is ideal. It's what we want. We don't have to worry about. We don't have to worry about internal resistance. We don't have to worry about the resistance of the voltmeter. State and explain how the current in the circuit changes as the thermistor is heated. Right, so what we say is, as the temperature increases, let's say, the resistance of the thermistor decreases. If the resistance of the thermistor decreases, the current in the circuit will increase. 3 marks. What did I write? Let's have a look. Temperature increases, the current increases because the resistance decreases. I didn't write it, I just cheated. Figure 4, calculate the voltmeter reading when the temperature of the oven is 240 degrees. We have to, that's 4 marks, look, so we have to do a few things. First thing, let's use the graph. Because we've got temperature, the only way into this question is to go from temperature to resistance and then have another think. So let's go 240 to nasty scale, 250, 225, 240 is 10, 20, 30, no wait, 10, 20, 30, 40 is there, come across here is 40 ohms. 40 ohms. Once we've got the voltmeter, calculate the voltmeter reading when the temperature is that. 40 ohms, what is it? 5B. 40 ohms at 240 degrees C. Now, we can use the potential divider equation here to get our voltmeter reading. That's the V out essentially, right? There. So it's our 200 ohms divided by the total resistance, which is our 40 ohms thermistor plus the 200 ohms, 240, multiplied by V in, which is 6 volts. So our V out, this is the potential divider equation here, look, V out equals R out divided by R total times V in. Put the numbers in, half a volt, 2 sig figs. That's it. C, an LDR is another component. Yes, it is. Copy and complete the blah blah. Let's not copy it. Let's just draw the symbol. Boom. There it is. State with a reason how the voltmeter reading varies as the light intensity. Okay, the voltmeter's there. Similar idea to the thermistor. Let's say the light goes. You have to decide what to say about whether you want the light going up or down. Let's increase it. Actually, the question is saying increase, so you don't have to decide. As the incident light increases, the resistance of the LDR decreases. If the resistance decreases, what will the PD do across it? It will decrease as well. Therefore, more of the 6 volts PD will appear across the 200 ohm resistor, which is where the voltmeter is connected. So the voltmeter reading goes up. Let's recap. The light increases, resistance of LDR decreases, so PD across it decreases, so voltmeter reading increases because the voltmeter isn't across the LDR, it's across the 200 ohm resistor, you see. State with a reason how the voltmeter reading varies as the done it. Right, that's the second time I've done that. Anyway, there we are. Better to do something twice than not at all. There are exceptions to that rule. Breaking a leg. No, you wouldn't want to. No, hold on, that's wrong. No, breaking the leg. That rule applies to breaking the leg. Forget it. Let's move on. This question is about possible heating circuits. To demist a car window. You have one of those in your car, if you have a car. Thin strips, blah, blah, blah. The potential difference across each strip is 12 volts, all right. 2 amps. Now, the car battery has an EMF and an internal resistance. calculate the resistance of one strip. Easy beginning here, question for 1 mark. Very straightforward. If it's 1 mark, it's straightforward, isn't it? R is V over I, 12 over 2, 6 ohms. Calculate the total, let's get you in shot. Calculate the total resistance of the heater. We want to do 8 strips, so it's 8 over 6 surely. Let's see what I wrote. Here we are, 6 ohms. Second part of the question, yeah, we can just go 1 over R total equals, what will you do? Instead of writing it out 8 times, 1 over 6 plus 1 over 6 plus 1 over 6, just write 8 over 6.0, gives you 1.33 recurring. Take the reciprocal, 0.75 ohms is the total resistance of the network. And calculate the resistivity. You've got the length, you've got the thickness and the width, which will give you the cross-sectional area. And we've just calculated the resistance of one of them. So use that. So you take your resistance equation from the data sheet and you rearrange it. Do the rearranging first, don't put the numbers in. It's good practice to rearrange the equation, then put the working out in. There's a resistance, there's the thickness and width, and here's our length. I have our powers of 10 in there, and it's 3.2 times 10 to the 6 ohm meters. And if you forgot that unit, well, then you would work it out from the equation. Ohms, meters squared divided by meters gives you ohm meters. 7a. 7. Question 7. It's a variable resistor across a battery with an internal resistance. Calculate the internal resistance of the cell. The EMF is 1.5 volts. This is set to 1 ohm and the current is 0.5 amps. So let's find the circuit resistance and take away 1 ohm. And that can only then be the internal resistance, because there's 2 resistors in the circuit. The internal resistance, that is the resistance of the cell, and the external resistance, the resistance of the variable resistor. So that if we get the circuit resistance and take away the resistor we know, we'll get the unknown resistor, right? It doesn't matter that it's internal resistance, it still works in the same way. R is V over I. V, 1.5 volts. I, 0.5 amps. It's the current in the cell, so therefore the current all the way around. 1 over 0.5 would be number 7. Here we are. 1.5 over 5. R is V over I. 3 ohms circuit resistance, so the internal resistance is 2 ohms. B, the resistance of this is varied from 1 to 4 ohms. This is a way of investigating the effect of changing the current against the power given out by the cell. Copy and complete table 1, and here we go. You can do that. The current, we know that the current for the external resistor 1 ohm, it's 5.5 amps. For 2 ohms, we go I equals V over R, where it's 1.5 volts over 4 ohms, because we know that the internal resistance is 2 ohms, and the was I still recording then? Probably. We know that the internal resistance is 2 ohms, and the external resistance is 2 ohms, so it's 4 ohms. That, which gives us 0.375 amps. I've broken my sig fig rule here. It should be 0.38 amps, shouldn't it? Because we've got 2 sig figs either side here. And at 4, it's V over 1.5 over 6, because it's 4 ohms plus the 2 ohms is 6 ohms. Circuit resistance 1.5 over 6, 0.25 amps. I squared R, boom, boom, boom. The power dissipated by the variable resistor is a maximum when the external resistance equals the internal resistance. This is always the case for a power supply. It is able to deliver maximum power when the when the load resistance is equal to the output resistance of the power supply. It peaks at that point. It's important in amplifier and loudspeaker design, for example, where you normally get your loudspeakers 8 ohms and you want the output resistance, or it's called output impedance, of the amplifier to be about 8 ohms as well, so it delivers maximum power into an 8 ohm load. Question 8 goes like this. Let's see if I can do this before the battery in my phone runs out. Circuit used to monitor the level of water in a container. Here's the container. 200k resistor, 9 volts. The battery has an EMF of 9 volts. No internal resistance, good. Voltmeter shows 0 volts when the contacts are dry. Of course it does, because it's an open circuit, isn't it? There's a gap here. So it's effectively the circuit is switched off. And 6.5 volts when the contacts are in water. Water is a conductor of electricity. Explain why the voltmeter reading is 0 when contacts are dry, because the circuit is open. Open circuit, I equals 0, so voltmeter reading is 0.0 volts. Calculate the resistance of the water between the contacts when they are placed in the water. Yes, so we would then 6.5 volts, right? So let's work out the current first. How many marks? 3. Yeah, let's work out the current first. It's going to be I is V over R, which is your 6.5 volts divided by the, yeah, that's right. The voltmeter shows 6.5 volts when they're in water. So the current through the circuit is the current through that resistor. So it's 6.5 volts across 200 times 10 to the 3 ohms, which gives us 3.25 times 10 to the minus 5 amps. And then the resistance of the water between the contacts, there's the same currents going through the water at that point. So we can go R is V over I, is we want the PD across the contacts in the water, which is the 9 volts minus the 6.5 volts, the voltmeter. So the remaining 2.5 volts is across here, divided by the same current, 3.25 times 10 minus 5, which is, and I've done this a number of times because the answers in the book are a power of 10 off this, 77 times 10 to the 3 ohms to 2 sig feeds. That is right. It would be, because look, you've got 77 kilo ohms there and 200 kilo ohms there, in the same ballpark. This is about a third of that, and the voltage is about a third of what it is across there, 2.5 volts, 6.5 volts. So that's absolutely right, and the answer is a power of 10 out in the answers online. And question part C, explain how the voltmeter reading would change when the contacts are in water and the resistance of the resistor is made smaller. Slightly confusing wording there, but what they're saying is put a smaller resistor in here. So if you put a smaller resistor in this, then the resistance of the water stays the same, but this resistance goes down, so more PD will be found across the contacts in water, less across here, so the voltmeter will drop. Involving current in the argument, we can say if the 200 kilo ohm resistor is reduced, the more PD across the contacts in the water because the current is increased. If you reduce this resistance stays the same, but the circuit resistance goes down. Current goes up, more PD across the contacts in the water here, and therefore PD across the resistor is reduced, because if more of the 9 volts is found across here, there can only be 9 volts shared between them, so this has to be less than 9 volts. So that is that. Well, I hope that was helpful. And that marks the end of our electricity. And next up is going to be waves. Speak soon.